Hello everyone, welcome back. So let's actually do a problem now and calculate some properties for our compressor. So we're going to have a multi-stage axial flow compressor. Don't worry about the multi-stage and axial flow, it's just a compressor. And it has a mass flow rate of 50 kilograms per second and a total pressure ratio of 35. That's nice, it gave us the total pressure ratio from the start. The compressor polytropic efficiency is 0.9. And the inlet flow conditions in the compressor is described by this temperature and this pressure. We're going to assume the flow is adiabatic, which we can do, that's fine. Has constant gas properties, that makes things easier for us. And we're going to calculate the compressor exit total temperature, its adiabatic efficiency, and the shaft power that is running this compressor. Okay, I feel like we can manage this. So let's see. First off, let's get that total temperature at the exit. Now, how are we going to do that? Well, you can remember that my total temperature ratio, this is actual, is equal to my total pressure ratio raised to that power. But since it's not isentropic, we have to add in that polytropic efficiency to correct it. I know my polytropic efficiency, I know my total pressure ratio, and I know my ratio-specific heats. It's air, we'll use 1.4. So I can plug this in, and I get my total temperature ratio across my compressor is 3.0916. Okay, so if I know that, I can then rearrange and say, okay, well, total temperature ratio, you're equal to my temperature after the compressor over my temperature before the compressor. And I know 2 of the 3 of these, so I can solve. I'll rearrange. That gets it in terms of those 2 multiply together, and I just plug it in. And so I get my temperature afterwards, 890.4 Kelvin. If we had a better compressor, this would be a lower temperature. Not down to 288, it's still gonna have to increase, but it'll be a lower temperature. Okay, so that's one of them. Now let's look on the compressor adiabatic efficiency, which is not hard to calculate. Why? Because we have it in terms of our total temperature and total pressure ratios, both of which we now know. So this is literally just plug and chug at this point. This is why we took all that time to calculate these things, because I don't have to worry about all the temperatures for each endpoint. I can just plug in my ratios. So I do so, and I get a adiabatic efficiency of 0.8422. You can see that that is different than this guy. And why is it different? It's different because my total pressure ratio is higher. So the higher your total pressure ratio, the bigger the difference between your polytropic and your adiabatic efficiencies. Okay, now how much work does it take to actually run this? Well, that's a measure of my mass flow rate and my change in enthalpy. I know my mass flow rate. I don't actually know the individual values for these enthalpy. But I'm saying it's a calorically perfect gas. We're assuming constant specific heats. And so I can say, okay, well, what's the specific heat of air? 1004 joules per kilogram Kelvin. And what's my change in temperature? Well, do I know that? That's a hard thing here. And the answer is yes, I do. I have my TT3 right here. I have 288 right here. If you wanted to, you could also get this in terms of the ratio, just dividing by TT2 inside of the parentheses. But that's kind of a weird thing to do. So I'm not going to worry about it for now. I plug everything in, and I get a power of 30.24 megawatts. As a note, if you're wondering where does this power come from, this power comes from your turbine. Your turbine's, most of its role is to run the compressor. By running the compressor, it is keeping your engine running, and by keeping your engine running, you stay in the air and you don't fall to your doom. So that's it for this time. Hopefully this helps you see how we can use the basic tools we've gotten so far to begin analyzing our compressors. Thanks for watching. Bye-bye.